think I'm gonna start with Lambda Calculus. This is Japanese lo-fi radio. Aesthetics, lo-fi, hip-hop, no copyright. 51 people watching. Lo-fi geek. I don't know, it sounds nice. So, Lambda Calculus. Yeah, I was thinking of something. Where is it? Next Rebel. So, someone commented actually, I read a comment on one of my posts about Lambda Calculus on Mastodon that, yeah, I was writing how I still have to go through the, like it's still not very clear, the chapter on booleans and how the select first, select second and cond and make pairs somehow create all these nots, ands, and ors. And it's, well, I guess it just takes time. It just takes time. And maybe like this. It takes time, but then I had an idea. To, yeah, and someone wrote a comment that the next part actually, which is about numbers, how to define, I guess, church numerals is the expression. It's very mind-bending. So that's kind of very nice. But I really want to be even better prepared before I tackle that chapter. Not sure. Sometimes I would just, I'm not, actually here, I'm not sure what's the right course. Should I just go to the next chapter or should I just really go through what I've learned so far? So I think I'm just going to go through what I learned so far, but like really skim through. I don't mean to like really read everything. And also I wanted to try to apply something like the next language itself. Okay, we have attributes. And something occurred to me yesterday to try out. I'm not sure how that will look like. I will use ChatGPT to help me to generate some of these, since it can do kind of well, you know. But even just to take the first identity, right? And right, it's just this identity, and then we have a or just like this, right? We could say it like this actually. We don't even have to name it. So now it's like an anonymous lambda function, right? We have the head here. We have the head here, the lambda head, which is the parameter, and here is the argument, and we pass in the 2, right? We pass in the 2, and the head gets discarded, and the x, instead of the x, we take 2. We put 2, and that's what we have. We have 2. So this is like the basic level, but Nix has attributes. So I was thinking you could also write something, because in some sense I want to understand Nix better, and there seems to be, I guess that's an idea, and how the code, the Nix code looks like with its heads and bodies. It looks like Lambda Calculus, and okay, it's purely functional and lazy. So that must mean that there are certain idioms that can be designed within it that can somehow relate to Lambda Calculus. And my feeling is that a good time investment in learning Lambda Calculus can really pay back, as they say, in spades after, you know. So in Nix we have this idea of an attribute set, but also a function which as an argument or as a parameter takes something. Well, this is an empty attribute set, and then it outputs what? It outputs this. So this is also right. I'm not sure if I could pass inside like this. Probably not. No, while evaluating the value passed for the lambda, expected a set but found an integer. But you can even make this bigger. So like this. Well, in some sense, like id, let's call it id, the identity is this, right? So now we cannot call it like this, expected a set, because it's expecting the set, right? Right? This thing. So now we have to pass in id and we have to give it something. What are we going to give it? Well, let's try a string, nix, unexpected, expecting a dot. Wait a second, is it like this? No, it's not like that. It's like this. No. Syntax error. Well, I don't know. Can I do some? Can I pass? Maybe I cannot pass into it anything because it's empty. That's interesting. So there is a notion of emptiness here. Emptiness. I mean, yeah, because I know I can do this. Id, let's say, okay, parameter, right? We do this. And parameter. No, I don't have to put this here. So now we have an id, right? And I could do id hello nix. Nope, it doesn't work. I have to put this. Probably have to do this. No, it doesn't work. Id hello nix. Oh, of course. Yes. Okay, so we did this. So I have to do id and open up a curly bracket and write parameter. So there's a lot more typing going on. So my idea was, okay, parameter equals what? Hello nix, right? Like this. And now I think this should work, right? Why am I doing this? This is almost like more typing. The idea was to somehow encode the evaluation steps, at least within almost like types. This is not types. These are not type annotations. But somehow, because I've noticed the more I learn, there are a lot of these substitutions and stuff, and a lot of it when you learn these, lambdas gets I guess because of the time when that was invented and such, you would keep everything in your head. So you wanted to have some kind of minimal, language and not to write so much or something. But now with computers, I guess you can, it's kind of almost practical to have, visually at least some kind of context. Otherwise, it's just, you define and as true, false, as we said, true, false that or something, true, false this, and true, false, I don't know why, and the true, and then you have to unpack what each of the thing means. Or even if I have conned, true, false, why. So I have to unpack what each of these things means and how they're defined, and then do the substitutions, and then I transform that into some false true. I don't know. This is now random. I'm not really, these are not the correct ones. But so yeah, I was thinking, could I maybe use Nix attribute sets to somehow encode some of these ideas, or like some of these evaluation steps? But I don't know how, So let's just read a bit, and I'll just try to use maybe ChatGPT a bit, because it's kind of, ChatGPT can do well lambdas, up to a point, I guess. I've tested it a bit, So in imperative languages, array elements, record fields are changed by successive assignments. Yeah, right. In functional languages, because there is no assignment. Yeah, there's no assignment. Well, we bind the function to a name though. Well, it doesn't change though. We don't update the name, so to say. Substructures in data structures cannot be changed one at a time. It's necessary to write down a whole structure with explicit changes to the appropriate substructure. Explicit changes, yeah. Explicit representations for data structures. They do not provide arrays because without assignment there is no easy way to access an arbitrary element. Of course. So this is an interesting point. Why does not provide assignment? Yeah, I don't know. There is no easy way to access an arbitrary element. What does that mean? It's like, I think it's yeah, I don't know. This is a weird. Certainly writing out an entire array with a change to one element would be ludicrously unwieldy. Yes. Nested data structures like lists are provided. Yeah, I don't know. Could I use lists for the identity? Like, how would you... Like, how would one define an identity in Lambda Calculus using lists and next? Because one of the ideas is to write some kind of tutorial for Nix language, because many people, they comment somehow about how the language is not pretty, but it's like, do you see the Lambda Calculus underneath? Maybe that would help. A function to apply to each element of the list, an initial accumulator, the identity function for lists, would return the list itself unchanged. You can represent this in Nix by a representation of a list in Lambda Calculus style. Make list f init, f1, f2, f3 init. Oh, identity function for lists returns the list itself. List. Yeah, look at this. The head, another head, another head, list f init. This is interesting. This is like a make pair function. Yeah, I remember reading in a type of programming it's a Haskell book by Lorenzo Carbonara. It's a very good book. A very interesting book, a type of programming. Lorenzo Carbonara. I bought that book. I bought Type of Programming. It's a very nice book. And it's kind of written in this reading style where you just read it like a novel, you know. But he really, it really goes, it starts really from zero. But it really goes into, you know, I wish I tried reading this book a couple of times and always something, you know, interfered or something. I just stopped. I'd like to read it. It just takes so much time to learn all of this stuff. It takes me years. And it's interesting, other people, like in a couple of years, they do so much. Wow. The identity function for lists would return the list unchanged. Apply identity make list. And interesting that the identity of a list is same as the make pair function. Because we have list f init, list f init. Example, apply identity make list. Oh, he's just making a list here in apply. Yeah, I thought like, is there a simpler example using lists? Identity xx my list 1 2 3 identity my list. Yeah, I don't think I can use this. Can I write comments in Nix? Multi-line comments, yes, multi-line comments. But some like comments, like, are there comments to describe functions? There is no built-in syntax for function documentation. Oh, there is no built-in. Yeah, too bad there is no built-in. Yeah. Okay, stop. Thank you. Call package. This is a talk I want to watch. So, a related difference lies in the absence of global structures. Yes, there are structures, but there are no global structures. I guess this, you gotta know what this means, I guess. In imperative languages, if a program manipulates single distinct data structures, then it is usual to declare them as globals at the top level of a program. Their substructures may then be accessed and modified directly through assignment within subprograms without passing them as parameters. So, if a program manipulates single distinct data structures, then it is usual to declare them as globals at the top level of a program. Right, this is actually how it works. It manipulates distinct data structures and you declare them as globals at the top level. And their substructures may then be accessed and modified directly through assignment within subprogram without passing them as parameters. So this is a completely different way of designing programs. In functional languages, because there is no assignment, it's not possible to change independently substructures of global structures. Instead, entire data structures are passed explicitly as actual parameters to functions for substructure changes, and the entire change structure is then passed back again to the calling function. So this kind of means that your building blocks are smaller. This kind of means that when you have, okay. So this kind of, this is actually very meaningful. So it's meaningful in the sense that when you design things, you don't design it like here's this global big thing and there's, yeah, I didn't really say much, but your building blocks should be small. And of course, small, what does it mean? They should do well, they're flexible and small, I guess. And so they're like building blocks. I guess it's a different way of thinking than having these global things and that gets updated and destroying the previous state. This means that function calls in a functional program are larger than their equivalents in an imperative program. Yes, also because of these additional parameters. Because you pass in the entire thing and you change it. That's why they have to be smaller, I guess. It has the advantage of ensuring that structure manipulation by functions is always explicit in the function definitions and calls. What structure and interpretation of computer programs, I think that was Abelson who said, how many things, like what's, or Sussman, no, that was Abelson. No, that was Sussman. He was saying like, what's hidden under the table, right? Since it's explicit, nothing is hidden under the table. He used that kind of interesting expression. This makes it easier to see the flow of data in programs. Also, so it's very explicit. So in many imperative languages, subprograms may be passed as actual parameters to other subprograms. So subprograms, I guess you could say, I guess what does that mean, subprogram? I guess a certain functionality of a program may be passed as actual parameters to other subprograms, but it is rare for an imperative language to allow subprograms to be passed back as results. Yeah, this is maybe not so clear. In functional languages, functions may construct new functions and pass them on to other functions. So my idea was that in Nix, I mean, some people complain about the language, but it's purely functional and lazy. and like it has these lambdas and everything. So basically you can design all kinds of things with it. You're totally free to design things, I guess. Maybe, yeah, I guess maybe the more complex things you design, you might notice the need to introduce certain functions, I guess, or idioms that would encapsulate some, you know, more complex behaviors. Functional languages allow functions to be treated as values. The following contrived illegal Pascalish function returns an arithmetic function depending on its parameter. Type, add, sub, mult, quote, function, arithmetic, op, type, function. Function sum, x, y, integer, begin sum, x, y, end. Function diff, x, y, integer, begin diff, x minus y, end. Difference. Function times x, y, integer, begin times x, y, end. And so with divide, begin case. All right, origins of functional languages. Yeah, look at this. Functional programming has its root in mathematical logic, in formal logical systems in use for over 2,000 years, but first modern formalizations were by Hamilton, De Morgan, and Boole in the mid-19th century. Propositional and predicate calculus. True, false as basic values. It's funny, like, did Boole actually, and the people, did they really, they didn't use lambda, like, how did they define true and false? I mean, I guess maybe they started with an assumption as basic values, and with and or not, and so on, as basic operations. So true and false are basic values. There's nothing else. And or and not, hence. Names that used to stand for arbitrary truth values. So names for arbitrary. Within propositional calculus, it's possible to prove whether or not an arbitrary expression is a theorem, always true, by starting with axioms, elementary expressions. It's also used to describe digital electronics, and on and off signals are represented as true and false. And electronic circuits are represented as logical expressions. So the predicate calculus extends propositional to enable expressions involving non-logical values like numbers or sets or strings. Quantifiers, quantification, number theory, Hilbert, Russell, okay, Turing, Lambda. Here now he's going, oh, an important difference between Turing machines and recursive functions and Lambda calculus. Hilbert's program had promoted vigorous investigation into the theory of computability to try to develop formal systems to describe computation in general. 1936, it's like 100 years, three distinct formal approaches to computability were proposed. Turing machines cleans recursive function theory. Yeah, Lisp was based on this at first, based on work of Hilbert, and Church's Lambda Calculus, each well defined in terms of a simple set of primitive operations and simple set of rules for structuring operations. Each has a proof theory. All the above approaches have been shown formally to be equivalent to each other and also to generalized von Neumann machines. Yeah, but the Turing machine approach concentrated on computation as mechanized symbol manipulation. based on assignment and time, ordered evaluation, time, ordered evaluation. Yeah, because Lambda Calculus, it's lazy actually. Yeah, it's not time ordered. Recursive function theory and Lambda Calculus emphasize computation as structured function application. They both are evaluation order independent. That's also interesting. Operational description. Vienna definition language, VDL. What kinds of, hi Dapster, nice to see you. What kinds of features would a Lambda Calculus interpreter need? What do you need by, you mean like idioms, or like what kind of, I don't, it's not really complicated, at least the simple one. It has really like 3 rules. I think he has just 3 evaluation rules, and you have variables and, you know, functions. It's really not, maybe there is, I think you may have to define the way how you would do recursion, I think. I'm not that far. So in some sense, you could say these are all combinators. So you would have to have some kind of recursion combinator, maybe the Y combinator. I'm not sure if that's supposed to be already implemented in the interpreter. Yes, I think it would interpret something. Yeah, you don't need if statements. There are no if statements. I mean, you can, the way how it's, I mean, you could define them, you know, but you don't need them. The Lambda Calculus can, so to say, have if statements without explicitly defining if statements, you know, like the way the control, like I designed, okay, the way I made make pair, the way I made AND is to use make pair and select first and select second. And if just by combining these 3, which I defined from nothing also, I got an if actually, I got a cond. And if you look at already a cond, that's an if statement. You see, I've just made from nothing. Everything what I had at start was the identity function. That's the kind of the mind-bending idea when you just, everything, like you try to grasp at something and everything boils down to empty function calls. Here I'm making an interpreter. Well, that's great. You may actually learn this in a, it's interesting, like you already, like I'm trying to like read about it and kind of make these interpretations in my head, but you're kind of implementing it. So that's kind of interesting. Well, have you looked at some of the code of some examples? Or maybe you can just think through it and then have this, you know, mind-bending, you know, moments. Someone commented on my post that now when that's why I'm going from the beginning again a bit. When now the numbers come, it will be really, you know, trippy. Yeah, I should probably read more on the Lambda Calc to get a better picture of what kinds of things go into interpreting the various kinds of expressions or statements. And no, I haven't checked out other people's examples of one. Well, that's also great. That's nice, you know. I I guess that's nice because you kind of, you skip some things when you do that, you know. It's good to spend some time. But look at me, I'm making, oh, this is already like 20th, you know, video of this, and you've been here a lot and you still have no idea what's Lambda Calculus. And there are all these people on YouTube who make very short videos on, but I mean, again, I don't want this to sound like I'm criticizing them, but they make this really short, you know, videos, and then the comments are like, wow, this is the best video, it's so great. But I don't know, this is like really hard. Have you looked at some other, you know, videos on YouTube where they, you know, like really explain, not like, you know, me, what's Lambda Calculus? And this is great to know, even if you don't do it, you know, even if you do Zig and stuff. I think this is really great because you'll get this kind of a lens that will indirectly work on whatever code you look at. Calculus. It looks surprisingly simple. So that's it. It's based on function abstractions to generalize expressions through an introduction of names and function. So it just has application, abstraction, and yeah, I'm making it in Zig. Zig has overcome C++. Oh, congratulations. I mean, I'm happy for you. It seems like you're happy about it, so that's great. It just has abstraction, application, and naming. It's like, it just has two things. Has a number of properties which suited well for describing programming languages. Abstraction and application are all that's needed to develop representations for arbitrary programming language constructs. Thus, Lambda Calculus can be treated as a universal machine code for programming languages. In particular, and also because the Lambda Calculus is evaluation order independent, it can be used to describe and investigate the implications of different evaluation orders in different programming languages. Because it's very simple, is relatively easy to implement. Can be used as a prototype run on a Lambda Calculus implementation to try the language out. So I'm still at 3, actually. We're going to look at it a bit now. And chapter 4, develop representations for recursive functions and use them to construct arithmetic operations. Chapter 5, discuss types and introduce typed representation for Boolean values, numbers, and characters. Already in 5, how can we introduce types? 6 will develop representations for lists. So you'll do lists in Lambda Calculus. Chapter 7, extend linear list processing to composite values. And look at trees. And then here different evaluation orders, termination, and then standard ML. And Lisp. Yeah, here also this has been used in that book 2015-16 from Alan and Mononoke, whatever, how is her name? Haskell programming from first principles, and sometimes this kind of example is used, like you do 10 times 9 and one thing changes, and then you put a name to the thing that it changes. He has this nice way of showing how to program replace items in 10 times items. So we have abstracted over an operand in the formula. We need to supply a value for the name, replace items with 84 in 10 times items. I guess this is a nice way how you can show someone how programming works. We have made a function from a formula by replacing an object with a name. Let us use abstraction again to generalize our example. Yeah, okay, replace cost, replace. This is nice. He really builds on this. Yo, there was a long chapter. Yeah, I kind of skimmed this through. I read it, but replace op, in, replace cost, replace items. He really builds on it. Abstraction based on generalization through the introduction of name to replace a value, and specialization through the replacement of a name with another value. Now I wanted to try something else actually today with the Nix attribute sets. I haven't used them here, so let's try that. Nix attribute sets. Right, that's the identity. Identity applied to the identity. Consider the function. Wait, I think I want to actually... where is the Alka crab? I really like that thing, Alka crab. Alka crab. Yeah, medieval, open ambient fantasy. Yes, the scepter of the celestial guardian. This sounds something for Lambda Calculus. Identity function. Yeah, I have a book for you, Dapster. I don't know if you've been here since the beginning. This is a very nice book. I don't think you read a book like this. A type of programming. I bought this book. I still haven't read it. It's a very nice book. It's a book on Haskell and functional programming, and it goes really far, but it starts from the bottom, you know. It's a very weird book in the sense that it's meant to be read. You kind of read it, and he really, I know this guy from Twitter, and we've also talked. Like he's nice, you know. If you want to know something, he will write back. So his name is Renzo Carbonara, and this book is meant to be read like a book, you know. He just talks about it. You can actually read here the first chapter, and it's nice how he writes it. It's not really, it's like, yeah, it's very interesting. Like, we can check it out. It's very unique. Like, I haven't seen a book like this, and you could just read it, like, you know, you don't even have to type anything. You could just read it through, which is very nice. Of course, after a while, I tried to read it, and I don't forgot of which part. But every time I learned something and I would reread it again. For me, it was too much to read the whole thing at once. I kind of lost it somewhere, but he really takes care. And I've read some of the people who read this book really liked it. And he really talks about types here just from the beginning even. He defines numbers and such. A bunch of books I already need to read, but something to just sit down with and just read. Leisurely programming books I'm reading, well, much more proactive. That's why I said, like, check this out. Like, it's really nice, and the chapters are short, so you can even, you know, read it in bits here and there. But it's very interesting. I think it's really helpful. Very interesting book. I'm curious, like, what you would think of it. It's almost, he has a way with words, you know. And there are all of these, yeah, it's very nice. It's not too fast. It's like subtle, and it's easy to get into it also. it takes care, you know. It's especially because it's not written for typing. It seems like he takes even more care, so it's like you can almost feel the code, you know, when you read it. Yeah, check it out. Very nice book. Very nice book. Yeah. Identity function. So the identity function returns whatever argument it is applied to. Yes. Suppose the identity function applied to itself. So I thought, right, wait a second. Identity function, right, x, 2. But how would it look like? Because x, now we have an attribute set. How do I pass in the 2? I cannot just pass in the 2. I was talking about PL design in a Discord server, and someone told me that I should learn Lambda Calc if I plan on writing a functional language, since it's really the backbone of languages like Haskell. What do you think? Oh, of course. Oh yeah, it's the backbone. It's really the backbone. It's like the machine code. It's the machine code. You know, and even if you learn you don't have, you know, like even if you learn some of it, it will be help you to understand, because it's a totally different way how you design things. It's more like you design little building blocks and you pass them back and forth, and it's very explicit. So it's a different way how you design things. But it will be really like, I didn't learn it at first. I was trying to learn Haskell, and then I tried to learn category theory. And actually it was very hard. So now when I've tried to learn it for like a couple of years. I was trying to learn it since 2016. 2016 I first started to learn. 2015, even 14 with Lisp a bit. Haskell, but it was a very slow journey. 2016 I started to learn more and more, and then I did categories, but it was just too much. I read it a lot, and I was looking at Bartosz Milewski actually lectures. Those are really inspiring. But after a while, I don't know if you know this Bartosz. He's this C++ guy who used to work as a C++ guy and a physicist. He has these actually lectures which are wonderful. And he's nice and takes time, you know. You can even check this out, but you probably don't want. But this is very nice stuff. This goes very over the top, but these are like, he defines things as some of the things that in programming that you already know, he defines them as equivalent to something completely different that you know from programming. So in a sense, you start to see it's very zoomed out, you know, level to look at programming and how to design it. Very zoomed out, very spaced out. It's high above abstract. And for me, it was hard to learn this since I never actually dealt with anything so concrete. So to learn this, it was too abstract, I guess. Although I enjoyed it because I was this abstract freak. I just enjoyed reading something I didn't understand. Yeah, actually I enjoyed that. Yeah, but it's weird. But it's okay. It's not weird. It's just like I enjoyed it. And I enjoyed also to listen to, you know, people that are interesting. Like, he's great. Look, I even have to put him now. Look at this. Wait.
They're different, but they were different because of unnecessary details. They suddenly become identical, right? Like if you have, let's say, 2 billiard balls of the same color, right? They are not really identical if you look under the microscope. They have different maybe scratches, maybe they They have different configuration of atoms, right? But you can replace one with another when you are playing billiards, right? So once you abstract, things that used to be different now become identical. This is why we have this notion of identity. And this notion of identity, because of abstraction, is always non-trivial. Okay, so there are things that are strictly identical, so like you can replace one with another and you won't notice any difference. But then there are things that are identical for all intents and purposes. Okay, and in mathematics, this is like a very, very important thing. That there is this distinction between it's really the same or it's not really the same, but we will look at it.
Right, if you just look at this now, I can't stop. I would just now, not stop this. I would just stream this. I would just stream me, watching this and commenting. He was saying, there are a couple of talks with him, he was saying that this is the future, actually, that the functional programmer, so to say, and there is more of it always, like each year, I mean, more of it in the sense that imperative languages are adopting more and more these functional programming, how to call it, idioms or constructs. So, and then the people have been speaking about how we will lose jobs, and not we, I'm not a programmer, but how programmers are going to lose jobs and stuff. But if you want to invest into something, it would be great to learn a little bit of functional programming and even this stuff. Yeah, I really don't have much experience in functional programming. My main experience has been with C++. Yeah. Well, you have time. You have lots of time. You're at the college, it's great. No, it's great, really. You have so much time for this stuff, but it will be nice, and that's also I remember Peter Norvig. I don't know if you know who is that. There's this famous, like learn programming in 10 years. I don't know if you know about this. Learn programming in 10 years. Teach yourself, yeah. Why is everyone in such a rush? This is, I don't know if you know this guy. He's the famous Lisp guy. He wrote the famous artificial intelligence book. And on Lisp also. He wrote this how to learn in 10 years. And here also he's saying that you should learn lots of styles, in the sense of, a lots of, where is he saying that? Language of choice, and he's mentioning scheme here, actually, also. To learn all kinds of styles, but he's also speaking about functional languages, and anyway. But what also Bartosz is saying is, this is very nice. It's just
as if it were the same, okay? And there is even a whole foundation theory that's being now developed that's based on like distinguishing between what's identical, what's not identical. It's called homotopy type theory.
Because you learned how to look at things through this lens. You don't have to really do this. Indirectly, you will tend to look at things you already do with a certain kind of lens that will naturally develop through actually, learning this stuff. And basically, it's just very mathematical. You see equivalences, what's similar, what's not, actually. And I noticed that with great also Nix people, how they basically, what everything boils down to, you see, it's like your lens can zoom into, deeper, and you can see what's actually different, what not. And anyway, now I'm really going off the rails here with this stuff. I really want to watch this.
It's a very hot topic right now in mathematics.
Like here he goes.
So you have object A, object B, and object C, and you have these two arrows. Then there always must exist an arrow that's a composition of these. So if I call this one F and call this one G, I'm using these names F and G that suggest functions, right? Because at some point this will be one of our models for a category. So this is called
Example.
G after F. After is this little circle.
Maybe here in the example.
So let me give you an example, okay? And this is the example that we'll be studying a lot because this is an example.
Maybe you will see something. I think he will talk about some table or like something.
From programming, right? We have a basic useful category that we use in programming. And this is the category in which objects are types and arrows are functions, right? Like if any single argument function takes an argument of a type A and returns a result of type B, right? So in the sense, a function is an arrow or a morphism between two types. So that's the category in which, this is actually in Haskell, it's almost exactly, well, actually maybe in ML, this is almost exactly the category with which you are working, right? Types are your objects, functions are your morphisms, right? In Haskell, it's a little bit more complicated because of laziness of Haskell. Okay, Haskell is a lazy language, so so the trick is that in Haskell, every type also contains this undefined value, the bottom value, which means like if you try to evaluate it, you will get into an infinite loop. It will take you forever. Because categories don't really take into account time. It's like time really is really hard to describe in mathematics, right? Whereas in computation, we worry about time, right? I mean, if something takes too long to calculate, that's useless for us, right? And in particular, if it takes infinite time to calculate, which means it never terminates, okay, it's a calculation. So if you have a function that goes forever, what's the return type for this function? It's a function that's supposed to return an integer, but it never does because it goes into an infinite loop. So in this case, in Haskell, we say it returns an int type, but int type contains this special value called bottom, which means it never terminates. Okay, and that's the digression I make once, and maybe from time to time I will say, well, of course, except for bottoms, and we are ignoring bottoms, or we are ignoring never-ending calculations and so on, right? So that there's this caveat. There's lots of caveats here in the beginning, and I would just want to get rid of them, and later we can think in simpler terms. Okay. But of course you might ask, but what are types, right? Okay, types in a programming language, what are they?
It's sets of values.
Sets of values. Okay, so there is a model, a kind of simplistic model. Maybe this works in ML. It won't work in Haskell because of the bottoms, right? But the simplest model for types is that they are just sets of values, right? And so we can model programming as in a category of sets. We can say, okay, so instead of types, we will be saying sets of values, right? And functions are just functions between sets. Okay, you can define functions on sets. Function from one set to another set, right? And that's a good model too. So sometimes I'll be talking about sets and functions. Sometimes I'll be talking about types and functions. And of course, when I say functions, I'm talking about mathematical functions, right? So mathematical function is defined between sets. So a function is just, you know, you take a value from one set and it gives you a value from another set, right? So I can even draw a picture of what I mean by a function in a set. So I hope you memorize the definition of category, right? I mean, it's so simple. It's very elementary. So I can erase this now. So it's like you have one set, you have another set. Here you have elements of this set, elements of this set. And the function sort of, you know, takes elements of this set into elements of this set. And again, I'm using the arrows. But these are different arrows. These are not morphisms, right? So one function corresponds to one morphism, right? But we can like, so this is another thing that you have to be very careful with. This schizophrenic view of a category, right? That every category, well, not every category, okay? But a lot of categories come from some model. For instance, you take sets, set theory, right? So, and you say, I'm going to represent these sets as objects in my category. This category, by the way, is called set. Capital.
Yeah, that was not actually. He's going. I could watch this, but I will not. That was not. I haven't seen this in a long time. I watched this a couple of years ago. There is an example where he, or maybe that's in the book also. There is a book, Barber's Paradox, language category like a graph, composable, bottom value. No, that's not here. Wait a second. Object, point, composition. Yeah, I don't know. Anyway, these are great videos. And he's nice to follow along. He has this stable level of, I don't know how to call it. Okay, I'll get back to my Lambda Calculus. So I was looking at how would I write it in attribute sets. No, actually that's wrong. I would have to write like this. Well, I could do like this actually, to declare two of these, and then like this, right? And then how would I pass it? Like this? No, I don't think so. Let's do one and two. I don't think this would work. Yeah, this is not. I think I need to put a comma here. No, this does not work actually. Yeah, I don't know nicks like this. No, this is not good. But it's just more typing. So these are applying identity to itself. Applying identity. Yeah, I'm not sure. How would I put these evaluation steps a little bit more, you know, explicit? Now he does the self-application. Self-application applied to the identity. Yeah, these substitution rules. I guess that's not possible. Just I could name things a bit more, but I cannot simply. Yeah. But this was clear. So it's almost like the variable in the identity is being applied to itself, and this goes into an infinite loop. But the context here is that this will become actually very important later, this idea of recursion, because something being applied to itself. Although this does not work in some sense, later more complicated combinators are going to be introduced that are basically based on this principle. Now he's just applying this thing to itself. So this entire thing goes inside of the S, and we remove the head, and you remain with this, and it kind of always goes inside, outside, inside, outside. It never terminates. Function application function. Yeah, so consider the function func arg, right? That's what we did, fa and fa. So apply, that's the apply equals fa, fa. So apply identity to 2, we get a 2. That's the same what we had before with identity 2. But now we have apply identity. Now I guess you might say, what do I need this for now? Apply. But again, it's some basic idea. Now, how would I write this with attribute set? Apply, probably like this. Fa. So this is the attribute set that takes the parameters, and now, yeah, I guess you could write f equals, what does it equal? Identity, right? And a equals, let's say 2. And I close it. Will that work? No, that will not work. Why does I think I'm missing something. I want to define apply in Nix language using the Nix attribute sets. And let's then do an example with identity. Apply identity. Identity 2. So I wanted to have the shape of like apply equals like this, fa, and then f equals something, a equals something, but there is a mistake, of course, with syntax here. Yeah, he's using let. It's nice. I think this would be a nice way to learn the Nix language. He's using the let. Let apply equals fa. Let result is fa. In what? F is f. A is a. Result is result. Define the identity function. Identity example. Apply f identity a2. I think I just, yeah, this is very long example. So would that be actually apply? But then I had to put 2 semicolons, I guess. Apply, let's do fa, and f equals identity. I guess I have to put here also a equals 2, like this. No, syntax error. apply. No, this is not. That's too much. That's too much. Just define it simply in one line as something like apply equals without let statements. First time chat, Agata Abigail. Hey, hey, hey. Hello, hello. How are you? I'm good, thank you. How are you? Apply. The concise version. Apply FA result. He's result as FA. Yeah, this is way more difficult than I thought, actually. Because apply... Yeah, this is too simple, but how would I put it in an attribute set? Apply in one line. FA, why result? Can we do it without the result variable? Yeah, like this, right? But that's FA. Oh, I was putting it in an attribute set, of course. So identity, just as our identity, let's call it identity prime, is parameter and parameter. Yes, and then identity prime, I guess I have to pass in like this, parameter equals hello world. Nope, wrong. Nope, wrong. Like this. Identity parameter hello world, hello world. So this is the same as before, but we had to pass in a set. So now apply, of course, apply, I was doing it wrong. Apply was apply and then FA and then FA like this. No. Yes, this is wrong. Why is this? How did I define identity without the semicolon? So then it means apply what? Apply. Well, of course, we cannot do now identity 2. Expected a set, but found a function. So we have to provide it. It's F, so apply F equals identity, I guess. And then a 2, and A equals 2. Will this work? No. Oh, I think it's this. Ah, okay, we found it. All right. So we define it like this. Apply FA. And that's actually important. I don't think I've seen that. This isn't the way to learn the next language, but this may be a very... Well... Apply, F is identity, and A is 2 semicolons. So that means you could do actually apply anything, right? You could do F equals, well, look at this. Let's define a double. Let's just try something. A double is lambda x plus x. So that means I can do now apply, F is double, and A is 2. So I should get a 4. That's nice. I passed it into an attribute set. And I have an apply function. All right. Func arg. Yeah, but these things will be, yes, that's part of the book where he really func arg, lambda, so the identity. And then here also the self-apply. So that's the self-apply, because the difference between applies, because we have two variables here that are, okay, we have two here, but these are different. These are called func and arg, but these can be called, you know, mumbo and jumbo. It's just, the point is that they're different. This one is the same. That's why this one goes into an infinite loop and this one doesn't, but it could, I guess. In this example of an application, the function expression is itself an application. Function arg, func arg, and the identity is here, which must be evaluated first. The bound variable func is replaced by the argument. Right, we substitute the func here. Although that's also inside of the body, right? Func arg, identity. So lambda x.x goes inside of func. We remove func. We remain with arg, identity, arg. Arg, identity, arg. Well, arg, func, arg. That's the body, but will be arg, identity, arg. Which is a new, yeah, probably there are these things. I should look at it again. Lambda Calculus visualizer, or like stepper. Oh, this is a nice one. Look at this one. You can see how they work. People have been working interactive. I guess some are dead links. Yeah. Wow, look at this. What is this? I guess some evaluation. Almost like that game of life thing. Chem Lambda, research paper. Wrote a research paper. Graphic Lambda Calculus. Visual language we can use to representing untyped Lambda Calculus. That's what we're doing. But it can be also used for computations in emergent algebras. Yeah, I guess that's interesting. I won't read this now. View PDF. Wait a second. Oh, he's doing it as graphs. Probably he put, look at this. That's interesting, but that should be, oh wow. Very beautiful. Association, co-association. I saw this with category diagrams, stuff like this. Ah, that's what they showed. Yeah, I know this game also, but I haven't really understood it well and I haven't played with it much. Alligator Eggs Interactive. Cube Composer, Lambda Circuitry. Lambda Animator. Does this work? Usage. Is there something in Nix packages? Lambda Calculus. Lisp interpreter written in untyped Lambda Calculus. That's something for you, Debster. Lisp interpreter written in untyped Lambda Calculus. Lambda Lisp written as closed untyped Lambda Calculus term written in a Lambda Calculus term. Lambda Lisp takes a string x as an input and returns a string as an output. Lambda Lisp. Shall P. What do I do now? Lambda Lisp BLC. There. Lambda Lisp BLC. Unbound. Yeah, I forgot Lisp. Is it like... No, wait a second. Like this? Wait, let's see if this works. I forgot Lisp. I mean, I didn't even know, but that little bit that I knew, I have no idea. Lisp. Yeah. It's written in Lambda. It's written in untyped. Maintainers, Kaf. Oh, I know this. Kaf. Christina Sorensen. Homepage. A Lisp interpreter written in untyped Lambda Calculus. Lambda Lisp. The entire Lambda Calculus expression is viewable as a PDF. Oh wow, look at this. Isn't this cool? Wait, I think this is... Wow. This is the entire program. That's a lot of lambdas. Can you believe this thing? This is totally... Look at this. This is a common Lisp program. This. This is a Lisp program. Just this. It works. References. Wow. A Lambda Lisp as closed untyped Lambda Calculus term. It's written as a Lambda Calculus term. Lambda Lisp, which takes a string x as an input, returns a string as an output. The input x is the Lisp program and the users... wait, I actually got a note. This entire computation process solely consists of beta reduction. Lambda Lisp presents a REPL where you can interactively define and evaluate Lisp expressions. But how did he write it? Supported interpreters are Justin Tuney 52 521 byte Lambda Calculus interpreter. The EOC most functional interpreter written by John Trump. The source is in the shape of a lambda. What are these? Who are these people? Oh, that's the picture from the Lambda Calculus is in 383 bytes. Why it matters. Binary Lambda Calculus. Meta Circular Evaluator 232 bytes. Yeah, this is a whole field, I think. Look at this, definitions. Oh, here you have some actual, what are these? Here are some important abstractions. That's the Lisp interpret. No, I'm not sure. Wait, nil, false, true. If omega, omega. Omega is the self-apply, I think, actually. I think it's called the omega. This thing, little here, this little thing, it's called the omega. It sounds like something from Star Trek. Car, cooter, or that's Lisp, and not XOR, bit XOR. Y. Here is the combinator Y. Look at it. This is how you do recursion. The numbers, that's what we're gonna do. Tooling, okay. Look at this. Nice, right? Let's make a screenshot. Screen. Maybe I can make an operating system that is purely designed to perform and evaluate lambda expressions. Haha. Yeah. But look at this. That'd be nice. Well, I'm sure there's great, value. This is nice. It even looks like a lambda. Yeah, I think there's it's a lot here. Trying out lambda, Lisp REPL. This works also. Yeah, okay. Well, I guess my plan of going through this has been 1 hour and 22 minutes. So introducing new syntax, notation. It's really hard, this lambda stuff. Yeah, the guy wrote to me, the Mastodon. No, I'm at Functional Cafe. What did he write actually? I will need to read that section again. The numbers one is the one that truly trips me up. Yeah. I'm reading from the start all over again until I cross over to numbers. Yeah. So the identity, the self-apply, and the apply. This is not hard stuff because, again, as I said, a lot of the things at this first stage is explicit. And the substitutions are not hard. But he does stuff like identity too. This is, yeah, I kind of missed this part. This is how you build abstractions, lambda x. Oh, so yeah, you could actually test this. So Nix REPL. So identity is lambda x dot x, right? But identity, let's call it identity prime. So he's saying lambda x. Oh, we don't have the apply. Apply FA. So identity prime is lambda x. That's how he goes on to define all new abstractions, but introducing the parameters that will be used within the body of the new definition. So you start with a new head, and then you reuse the definition you already have with the new, the unknown, how do you call it? Like the lambda x. and then he does apply identity x. So this will work actually, right? I mean, you could say apply as I did before. That's what I was doing before. I defined identity and apply, and then I did apply identity 2. But of course, to put a name to this is exactly to do this. Identity prime, let's call it 2, and x, a lambda x, apply identity x. This is much, okay. You see, these are very little things. I've defined an abstraction here, and then I've used it. And then a 1 here, and then I've combined them with a value. But I could have defined a third abstraction that abstracts over this itself, which is identity 2 lambda x, apply identity x. And now identity 2, well, I could write identity 2 hello Nix. And I still have the same thing as apply identity hello Nix. But this is not the same. Yeah, that's why it's good to go from the beginning, I guess. Maybe not before each chapter, but let's apply this to the identity function. Now he applies this identity 2 to the identity. But I cannot do just this because I'll get a lambda string because I have to provide it some kind of value. So I could do identity 2 identity 2, and I still get a 2. I could do identity 2 identity and apply it to apply identity hello Nix. Will this work? It does work. Identity 2 identity applied to apply identity hello Nix. An operating system that is purely designed to perform and evaluate lambda expressions. Well, that's what I was saying to you. I would like to have a game because a lot of these steps are, well, they are explicit, but you as a programmer, somehow they're not so explicit. A lot of the stuff, it's contained in the head, and when you look at the code, you need someone to explain it to you. Although it's implicit in the, yeah. What I mean to say, it would be nice to have some kind of 3D game that would show all of these things, that you can at least look at it. I think it will be helpful. It's not something that you would, it will be, I don't know, that's like my secret wish. To make sort of a game, because there's so much text on so many sides. Be nice to see it in a certain way. Okay, identity to identity. Okay, that was actually helpful. Apply identity and then identity. Yeah, but it's hard to encode this thing because, for example, here, okay, there are 3 names here. And now we expand on the apply. We look at the function definition. Identity. Now substitution. Yeah, that's hard. How would I write that? Because the identity now goes into the function. Here we drop the func head. We have arg, identity arg. Again, identity goes inside of arg. We drop the arg. We have identity applied to identity, and so on, right? Because we have the, now we can substitute. He's not showing it here because this kind of, it's already simple, but identity is lambda x and x. So the identity goes inside of the x. You drop the lambda head and you are left with identity. All right. Yeah, I think I'll stop with the Lambda. I'll just make a short pause and then I'll be back. Maybe I'll just surf a bit and watch what's on Nixos, you know. So that's it for now. I'll be back in a couple of minutes. Bye bye.